The Paragon M841 is a mobile offshore drilling unit, or MODU. A MODU is a platform designed to be moved from one drilling location to another, a 6,600-ton example of sophisticated offshore engineering. The core paradox of this structure is that it must operate within two entirely different physical domains. While moving between sites, it is a free-floating vessel subject to the fluid dynamics of buoyancy and hydrodynamic drag. However, once it reaches its destination, it transforms into a fixed offshore tower, engineered to resist the extreme environmental shear forces of wind and ocean currents as a static structure. To drill, it must elevate its massive 18,400 kip weight above the water. A kip is a unit of force equal to 1,000 pounds, meaning this rig suspends over 18 million pounds on 3 steel legs. Survival in these environments relies on absolute adherence to an operational state machine. Every move is dictated by the rigid mathematical boundaries defined in the rig's operations manual. We will trace the life cycle of this deployment, from the stability limits of transit, to the proof testing of the seabed, and finally to the statics required to survive a 100-knot storm. Offshore engineering requires a structure capable of navigating these two distinct physical states without compromise. In field transit mode, the rig floats on the surface with its 500-foot legs raised. This minimizes water drag, but places a massive amount of weight high above the waterline. The primary constraint here is intact stability. The crew must resist the overturning moment generated by wind heel, the force of the wind pushing against the surface area of those raised legs. Stability depends on the vertical center of gravity, or VCG, and its relationship to the metacentric height, known as GM. VCG represents the concentrated weight of the rig, while GM is the distance from that center to the metacenter, the point where buoyancy vectors intersect as the hull tilts. Lowering the legs improves stability by lowering the VCG. If the base of the legs is 12.19 feet below the hull, the rig can withstand 50-knot winds. Lowering them to 93.87 feet secures the vessel for winds up to 70 knots. For long-distance ocean transit, the constraints are even tighter. Crew must physically remove upper leg segments to stay within the rig's motion limits and avoid structural failure during the tow. These adjustments are time-sensitive. Because the legs cannot be jacked up or down while the rig is under tow, every mode change must be executed before severe weather arrives. Towing a MODU is an exercise in active physics management, where the crew must constantly defend against the risk of capsize. Once on location, the rig begins the transition from a floating vessel to a bottom-supported structure by lowering its 3 spud cans to the seabed. Moving these 500-foot legs requires enormous force. The M841 uses 12 electromechanical rack and pinion units, driving the legs at a speed of approximately 1.5 feet per minute. This descent is only permitted if the seas are under 5 feet. Any higher, and the motion of the hull could cause the legs to strike the bottom with enough force to cause structural damage. Levelness is critical. The hull must be maintained within 0.3 degrees of level throughout the jacking process. If the hull tilts beyond this narrow tolerance, the legs will bind against their guides, causing the jacking mechanisms to jam or fail. As the legs descend, the crew must ensure the spud can vent valves are open. Without proper venting, the cans would implode under the sheer hydrostatic pressure of the deep water. This brief window between floating and fixed is the most mechanically vulnerable moment in the rig's operational life. Once the legs touch the bottom, the crew must verify that the seabed can support the rig's weight even during a major storm. They achieve this through the preload protocol, deliberately taking on thousands of tons of seawater as ballast to simulate the maximum loads the rig might encounter during a hurricane. The engineering goal is to generate a minimum reaction of 12,123 kips of downward force on each individual leg. This machinery deck plan highlights the specific outer hull tanks used for this process. By filling tanks like 21, 27, and 29, the weight is distributed directly over the legs to maximize the pressure on the soil. This extreme weight is held for at least 1 hour to force the seabed to consolidate. This prevents a punch-through, where a leg could suddenly sink through a weak layer of soil during a disaster. There is a critical mechanical limit here. The rig cannot be raised to its final air gap while carrying this preload water. The jacking pinions have a lifting capacity of 338.5 kips each. Carrying over 12,000 kips per leg would far exceed the design limits of the motors and gears. Preloading is a process of controlled structural trauma, forcing the seabed to fail under safe conditions so it remains stable when it matters most. After the preload is dumped and the hull is jacked up to its 40-foot air gap, the physics of the rig change again. It is now a fixed structure governed by statics. In the drilling condition, the rig must support dynamic loads, the weight of the rotary equipment, massive racks of drill pipe called setback, and the downward tension of the hook. To reach the wells, the cantilever and drill floor can skid a total of 70 feet aft of the transom. This moves the center of gravity significantly toward the rear of the rig. This shift in mass multiplies the reaction force required by the two aft legs. The further the cantilever extends, the more the aft legs must work to prevent the rig from tipping. The drilling weather curves establish the operational boundaries for these unbalanced loads, generally capping operations at wind speeds of 70 knots. If winds are forecast to exceed that limit, the person in charge, or PIC, must begin a transition to severe storm mode. The PIC is the designated officer responsible for all safety and operational decisions on the rig. This reversal involves skidding the cantilever back to its stowed position, removing pipe loads, and dumping supplementary variables to rebalance the rig. Surviving a benchmark storm depends on reverting the rig to a perfectly equalized 18,400 kip static load, distributed evenly across all three legs. Once the job is done, the crew must reverse the entire process to return the rig to its floating state. Extraction is hazardous. As the hull is jacked back down into the water, the buoyancy of the hull pulls upward, but the spud cans are often suctioned deep into the seabed mud. Tugs must only provide station keeping during this phase. If a tug tries to pull a stuck rig, the resulting tension can shear or collapse the legs. To break the suction, the crew uses high-pressure water jets built into the legs, blasting water into the mud layer at the base. This jetting fluidizes the seabed, replacing structural friction with liquid lubrication until the legs can be pulled free. Once the legs are clear, they are raised to the full tow position, returning the rig to the hydrostatic limits of its afloat condition. The Paragon M841 navigates the boundary between floating and fixed states, surviving through a strict and uncompromising adherence to the mathematical limits of its operational state machine.